Hello and welcome to the last Dorks of season 1. Today we have Space Part 2. My co-host, Scott Solomon, is on a much-deserved vacation with his family. So he's not part of this particular episode. And he's usually the guy who handles the recording. And I'll be honest, I blew it at the beginning. I missed the intro and I missed the part where we talk about what we're drinking, but I got my act together in time for the first talk. So we're going to jump right into the first speaker, and I hope that you enjoy the last Dorks of season 1. Let's get started. So I am super excited about the talks today. The theme is space. So we've got two awesome space people. Our first presenter today is Matthew Berger, and I am going to pull up a picture of the epic project that he has been working on over the pandemic. So first I'll say that Dr. Matthew Berger works at Space Telescope Science Institute. He's going to be talking about Mercury's atmosphere because yes, Mercury has an atmosphere, and he's upped his game during the pandemic by making a nice big smoker. So here, I'm going to share my screen so that you can see a picture of this amazing smoker. So here it is. All right, so Matthew, tell us, what is the most awesome thing that you have smoked in this homemade smoker?
Let's see. Tomorrow I'm doing a duck, so that should be good. This is the best way to make brisket, Texas-style brisket, and I did roast a wild boar roast that I got at Wegmans. And it didn't come out very well, but at least it was interesting.
That is interesting.
I overcooked it. I think it didn't get moist like a pulled pork.
So you mentioned brisket. Have you ever lived in Texas? And is that where you picked up brisket, or are you just?
I'm originally, I am originally from Texas. I grew up outside of Dallas. But I guess I didn't really appreciate the barbecue until recently.
That's a shame.
Yeah, it is.
Yeah. Barbecue is one of the best things about being in Texas. If you are a meat eater, I married a non-meat eater, but whenever we'd have a seminar speaker come through, we would often go for barbecue, and that's when I would get my fix. But your smoker looks totally epic. I'm totally jealous. I think one day I will probably try to tackle a project like that, but that's not what I was doing this pandemic. But yeah, let's see your presentation.
Okay. Do you see me? See it?
Yep, I see it. Looks great.
This. Sorry, there's a menu bar in the middle of the screen. Okay. So I'm going to talk about Mercury's atmosphere, and it's not an atmosphere like what the Earth has, but I hope I'll be able to explain why it's interesting and what we can learn from it. Okay, so first of all, an introduction. I'm originally from Texas, like I said. I have a BA in physics from Rice in Houston. I have a PhD in astrophysics and planetary science from the University of Colorado in Boulder. I did postdocs. I spent 10 years as a soft money researcher at the NASA Goddard Space Flight Center in Greenbelt. Soft money means fully grant supported. So it got difficult. It got painful. I'm trying to live completely off of grant money. And so I stopped doing that. And currently I'm at the Space Telescope Science Institute in Baltimore. My primary job is as a manager and operator for the data calibration and archive pipelines for the Hubble Space Telescope and the James Webb Space Telescope. So basically what we do is when the data come in from the spacecraft, we make sure that they get calibrated and then archived into MAST, which is the Mikulski archive for space telescopes. And then our users can retrieve the data from there. And I'm not going to talk about anything about James Webb Space Telescope because we're still in commissioning and I'm not allowed to, but the first science data will be released at the end of the commissioning period, which should be at the end of June. And I also buy back up to 20% of my time for science with grants that I'm co-investigators on. Just a couple websites for plugs for Space Telescope and for MAST. And this, if you haven't seen this, this is this image was just publicly released a few days ago, showing the alignment of the telescope, and you can find online comparisons with previous IR observations, and this is a really impressive image. So basics of Mercury, and I'm sorry that I'm going to be talking quickly. I have a lot, and I wanted to get in. So Mercury is the closest planet to the sun. It's about 4/10 on average. It's about 4/10 of a AU from the sun, which means it's where AU is an astronomical unit, is the distance from the Earth to the sun. It orbits in 88 days. It has a rotation period of 59 days, and there's this resonance that 2 Mercury years is exactly equal to 3 Mercury days. It's the smallest planet in the solar system, the 11th largest solar system object. It has an elliptical orbit, and this is important. The elliptical orbit is going to be very important for what I show, but for what I'm doing, it varies from about 0.3 to almost 0.5 AU. It's the most elliptical planetary orbit in the solar system. And then the surface temperature varies considerably whether you're in direct sunlight or on the night side. It's also the smallest object known to have an internal magnetic field. The data I show is almost all from this messenger spacecraft, and I don't really have much time to talk about it, but this is a surface map in exaggerated color taken by messenger. So this is really most of what we know about Mercury really is from the messenger spacecraft. Messenger is, I don't have much time to go over it, but the Mercury surface space environment geochemistry and ranging mission. It orbited Mercury for 4 years from 2011 to 2015, and in which case it made a hard landing with the surface. Couldn't maintain orbit anymore. All of the data, virtually all the data I talk about, and this is the instrument I work with, is the Mercury Atmospheric and Surface Composition Spectrometer. That instrument had 2 detectors on it, and all of my data is from the ultraviolet and visible spectrometer, UVVS. So I don't really have time to go into the instrument very much, except I'll show a few things that will help you understand what the data looks like. Okay, so the atmosphere. Mercury's atmosphere is what's called an exosphere. So an exosphere is the thin collisionless region of the atmosphere. It's the uppermost part of the atmosphere. What Mercury has is called a surface-bounded exosphere, which means it's collisionless all the way to the surface. In the exosphere, atoms are on ballistic trajectories and they don't interact with each other. So we can, if I want to understand, I can model sodium atoms. I don't need to worry about what's happening with any of the other species in the exosphere. They essentially are all independent of each other. Each atom is independent of each other. There's really no pressure. There's no atmospheric pressure because that depends on collisions. And because they're on ballistic orbits, the species in the atmosphere are being constantly created and lost. A quick comparison with Earth's atmosphere. Earth's atmospheric density is 2 times 10 to the 19 molecules per cubic centimeter. Mercury at the surface is only 10 to the 3rd to 10 to the 6th, 1,000 to 1,000,000 particles, atoms per cubic centimeter. The Earth's exobase starts at about between 500 and 1,100 kilometers, which is above the orbit of the International Space Station. And as I said, Mercury's exobase, that's where the start point is at the surface, 0 altitude, 0 kilometers. So what's interesting about this? So the Mercury's atmosphere it's in constant battle between the source and the loss processes. Some of the sources include micrometeoroid, I'm using the technical names are micrometeoroid impact vaporization, which is dust impacts. These are it's the same kind of dust that creates shooting stars, but on Mercury, they go all the way down to the surface and they kick up material. But it's like micron-sized dust particles. Photon stimulated absorption. This is when solar ultraviolet photons kick atoms off from the surface. They deposit energy and kick them out. And there's ion sputtering, which is the same sort of process, except that it's solar wind ions that hit the surface and kick things out. And that's more energetic. That's a more energetic process, so it can kick things farther. And ion sputtering is really interesting because it can only happen in certain places. This is a schematic of Mercury's magnetic field. And I'm sorry, it's kind of dark. But you can see that there are regions, you you can see that there are regions up near the pole, near the poles where there are some field lines on the day side that are closed loops, and then on the night side they're open. Solar wind ions can only get down to the surface in those regions, in that region between the open and closed boundaries. That's called the cusps. And this is the same. This is basically the same reason why we have auroral arcs on Earth, is that the solar wind ions can only get down to the surface, or get down to the atmosphere in those regions, and that's why the aurora and the poles. So if we see sputtering, then it tells us something about what is happening with the solar wind and the magnetic field. The main loss mechanism is photoionization. This is just where solar ultraviolet photons ionize the exospheric atoms. And then once they're ionized, they get what's called picked up by the magnetic field. And if they're on the day side, they might return to the surface, or if they're still within the magnetosphere. Sorry, not necessarily the day side, but if they're still within the magnetosphere, they might get returned to the surface, or more likely, they're just going to be swept up and taken away down with the solar wind. So because the exosphere is originating at the surface, it's a probe of the surface composition and also the surface physics. So things like photon stimulated absorption is a chemical process, basically. And so you're learning about the chemistry of the surface, how the surface interacts. It depends on things like the grain size in the regolith, things like that. We can learn a lot about the relationship with the sun and the solar wind and Mercury. So there's a lot of plasma physics going on in there, and the exosphere is a probe of that. And really, we're seeing the ongoing evolution of Mercury's surface. So things are still happening on Mercury. The surface is not geologically dead. Well, it's geologically dead. It's not chemically dead, I guess you could say. So what's in the atmosphere, the exosphere? So Mariner 10, which was the first spacecraft to Mercury, saw hydrogen and helium, which were basically implanted on the surface from the solar wind. They're not endogenic. They don't start there. They came from the solar wind. From the ground, sodium, potassium, calcium, and there's a possible detection of iron and aluminum. And then with MESSENGER, and this is what I've been involved in, we discovered magnesium, manganese, aluminum, and then there's ionospheric species like calcium plus, oxygen plus, and sodium plus. The main things that we observed during MESSENGER were sodium, calcium, and magnesium. Those are very bright, and it's just physics that let us observe those. The most abundant species is most likely oxygen, but it's extremely difficult to observe. So we don't really have observations of oxygen. We know it's there, but that's about it. But those three species I mentioned are what we observed every day over the course of the mission. Oh yeah, okay, that just highlighted those three. Okay, so let me throw some quantum physics on you. This is how we observe. This is why we're able to see these species, these different atoms. It's called resonant scattering. So you start with a photon from the sun coming in at exactly the right wavelength, and it hits an atom that's there. And if you can remember the Bohr atom, the electrons are in shells around the nucleus. So when that photon hits the atom, it absorbs the photon and bumps the electron to a higher energy cell. And then almost immediately, it re-emits the photon, or a different photon, but the photon at the same wavelength, and the atom goes back to its ground state. And that when it's re-emitted, it can go off in any direction. And so if you're off to the side, you can see that. And this is how we're observing all of these species. But here's what's really interesting. Photons have momentum. So all the photons are coming in from the sun. So there's all this momentum that the photons all have momentum that's directed radially away from the sun. When they're re-emitted isotropically in the atom's rest frame, which you can think of that approximately as Mercury's rest frame. And so there's zero momentum. That momentum has to go somewhere, and it's absorbed by the atoms. And so these atoms then get pushed backwards due to what we call radiation pressure. So here's an example. This is a simulation where I just sent particles, sodium atoms at 2 kilometers per second radially outward from Mercury. Mercury's escape velocity is 4 kilometers per second. So these go up and they come back down to the surface. And that's why it just looks like lines, because it's going up and down. If I turn on radiation pressure, all of a sudden all these sodium atoms get pushed back into a tail. And this is the exact same process that forms a comet tail, the neutral tail on a comet. Comets have an ion tail and a neutral tail. This is what forms the neutral tail. It's the exact same process. And so the one thing that's really important is that the strength of the radiation pressure depends on the number of photons that it sees at that exact wavelength. So as Mercury orbits the sun, because it's an eccentric orbit, the radial velocity of Mercury relative to the sun changes. So these arrows, these blue arrows, show how many photons are available at the rest frequency at 0 when the Mercury isn't moving relative to the sun. As Mercury moves towards, closer or farther away from the sun, you start moving away from those low points and move up into the wings of those absorption lines. That's a solar spectrum showing sodium absorption in the sun's atmosphere. And so as you move out, you might move, when you start having larger radial velocities, you have more radiation acceleration. So this is the plot on the left shows how much the radiation acceleration changes over the course of a Mercury year for those 3 species. And this is a model simulation of sodium over the course of the year. And you can see the atmosphere gets brighter and larger. The tail area gets brighter and larger as the year goes on. And it actually can go out to, it's actually been seen out to about 1,500 Mercury radii. And this is only showing plus or minus 10 Mercury radii. This one goes out to 1,500 Mercury radii. And this is a ground-based observation from Schmidt et al., a group at Boston University. Okay, so now I'm going to start. Let me talk a little bit about the messenger observations. UVVS, the ultraviolet visible spectrometer, was what's called a scanning grading monochromator. So it scanned in wavelength across the emission line and could only observe one exospheric line of sight at a time. So this is showing sort of our pattern. The one on the left shows we would alternate between observations of sodium and observations of calcium, for example, over the course of an orbit. And then on the right are sample spectra. So sodium is really bright. The solar background that you have to subtract off is very small for sodium. For calcium, the solar background is actually very large. The red line in that is actually the solar spectrum. The blue line is what we observed at Mercury. And it's just the calcium emission just sort of fills in the bottom of the solar line. So it's really difficult to figure out how much you have to subtract off. And so a lot of work has gone into doing that. And then each orbit, let's see, how do I start this? Each Mercury orbit has a different observing geometry. Like I said, we only observe one line of sight at a time. This is what a typical orbit worth of observations would look like for our instrument. And the reason is that it wasn't independently we couldn't independently point it. You had to actually turn the spacecraft to look at something. If the other instruments want to look at things too, so we're always competing for telescope time. And to be honest, the pictures of the surface really got higher priority than observations of the exosphere. So a lot of times we're looking in just random directions while they're pointing at the surface. On the night side, we had a lot more freedom because those other instruments didn't have any light to observe with, so we were okay. We were okay there. So you can imagine this is very difficult to interpret what you're seeing when you just plot up the data, and it's going to explain why we don't have any pretty images of the exosphere. Because we're just piecing it together from all these assorted views. So I'm going to talk about calcium now, I think, for the rest of the time. Calcium is really what I worked on. So I know the most about, this is really what I know about. One thing we saw from daytime limb scans, observations of the daytime, is that there's this persistent dawn enhancement in the calcium. This is the white dots are where we actually got spectra, and then the color is interpolated between those. And the unit is some weird thing called a kilorayleigh, but it's just a unit of light emission, essentially. And then, so showing it over the course of a year or so, Mercury year, a couple Mercury years, you can see that it's always there. It's sometimes brighter, sometimes fainter, sometimes it seems to spread out more, but it's pretty consistently seen. It was extremely repeatable from year to year. So this shows compilation of 9 Mercury years. On the left is the brightness at the surface, and you can see from year to year it's almost repeatable. But there is a strong variation with year. The scale height is a measure of how quickly it drops off, and that was relatively constant. And then the column density on the right, that's the column density at the surface. It's like the line of sight column of calcium. And it varied, you can see that it varied a lot over the course of the year. That bit in the middle is not real. That's because you can see on the left side that the brightness is really low in that area, and I'm dividing small numbers by small numbers, and there's very large error bars. So that's not real. But the peak at about 30 degrees true anomaly angle. True anomaly is the measure of it's the measure of where it is in its orbit relative to the closest point from the sun, perihelion. So you can think of this, we can determine, the source rate or the total calcium content in the exosphere. This is, so at its peak, the peak density is only like 4 or 5 calcium atoms per cubic centimeter. That's just insanely, that's very small. You can take a cubic centimeter and individually count the atoms in it. It's very small. The calcium content, it varies between, I think 15, what is it? I can't, the picture. I think it's 1,500 and 7,500 gallons of milk over the course of a Mercury year. So it's not very much. The total mass gets to up to about 35 kilograms at its densest. That's the total amount of calcium in the atmosphere. You could lift it. So why do we think this is happening? We think that most of the calcium comes from impact vaporization, and then the impact vaporization produces molecules like CaO, CaOH2 at about 5,000 Kelvin. And then those quickly dissociate and give I didn't mention this, but the exosphere is also very, very hot, like 50,000 Kelvin. We're not exactly sure how it gets that much energy, but it could be from these molecules breaking apart. And then near perihelion, which the closest point in the surface in the year, Mercury intersects a dust stream from Comet Encke. So these are some models showing the evolution of that dust stream from the comet. And these are this dust stream. This is the same kind of thing that produces the yearly meteor showers. The Leonids or the Perseids. Those are from the Earth intersecting comet dust streams, and the dust from those burns up in the atmosphere and produces shooting stars. Here, what it does is it hits the surface and produces a peak in the exospheric production. And we see a similar thing from magnesium also. Magnesium distribution is a little different, but it does show a peak at this same region. Sodium is much more variable. We're still trying to piece together what the sodium is doing. So my takeaway, for 4 years, there was a spacecraft orbiting Mercury that observed calcium in the atmosphere every single day, just for me. I didn't say this, but Messenger had a 12-hour, for the first year of the mission, there was a 12-hour orbital period. And for the last 3, it was an 8-hour orbital period. So it was just going around, observing calcium all the time. And I was really the only one looking at it. And then I'll add with a gratuitous picture of my children reflected in the James Webb Space Telescope mirror. This was in 2017 when they were doing testing at NASA Goddard. And that's all I have. Thank you.
That was awesome. Thank you. That looks like it's really hard to get those data. It's like super impressive that we have it.
Yes.
Yeah. So I'm going to selfishly start with a question that I have about space settlements. Oh, so first, Ada, do you want to show your artwork? So Ada does a little piece of artwork for every presentation that we have. And so here's Ada's. We've got Mercury with an atmosphere and the sun sort of blowing stuff away. And
wait, I just read an atmosphere and I just.
And she wrote atmosphere.
I just drawn Mercury and stuff.
Yeah, she drew Mercury and the sun. Anyway, it's pretty awesome. So I'm writing a book on space settlements, and so my questions revolve around life on Mercury and what kinds of things we might go to Mercury to mine. And it sounds like we wouldn't bother going to Mercury to mine it for calcium because there's not really that much there. But I did read a proposal where they were saying that if you wanted to have a settlement on Mercury, you could have it at is it called the terminator, the point where you're in the shadow between day and night and the temperature is a bit more mild? Is that what that's called?
That is what it's called, but it moves.
Right. And so the idea is you'd have to move your entire settlement to constantly stay in that terminator. Okay. And I should say, I don't think it's going to pan out, but what do you think?
I don't think it would be warm. I mean, I don't think it'd be moderate temperature because there's no atmosphere. There isn't enough atmosphere to hold in any heat. So, I mean, it does transition from really hot to cold, but I think it's probably a pretty sharp transition. So I don't know.
Okay, so you don't think that there would be a big moderate space where you could set up settlement? You think that, like, if my house is here and your house is there, my house is on fire and your house is a block of ice?
Yeah, there is some transition because the sun gets, there is some transition, but you still wouldn't have any, you'd still need protection from, UV, from solar wind, from everything. Vacuum space.
That's the problem with all of these proposals. Because you still need protection from space.
The moon is miserable. The moon has a similar sort of exosphere, sodium exosphere, and other species. You see it's in vacuum. You're still basically in vacuum when you're on the moon. The moon also has a sodium tail that can be seen.
And so is there more sodium on the moon?
I don't think there's more, and I believe just because the sun is farther away. Well, there's two effects with being farther from the sun. You have less production because it depends on the if it's depending on solar photons to hit the surface and knock things up. There's less source, but there's also less loss because there's less photoionization. So those things balance out. I guess it's similar to theirs.
Cool. Okay. I've got a question from the audience, but Sarah, did you have a question that you wanted to ask?
Not really a question so much as a comment. One of my favorite books that I have to Google what the plot was every time I read it. That's part of it. Actually, it's like a major motivator for the plot is having a city on the Terminator and there's like tracks around the whole planet. So I heard what you guys were talking about. I was like, oh my gosh, this is exactly like the start of 2312 by Kim Stanley Robinson. A book that I have to Google the plot of every time I read it because it is so hopelessly convoluted, but the world building is really good.
I've read the series about Mars, but I haven't read the book that you're talking about. So I'll have to check that out. So Hannah, who is a D.O.R.K.S alumna, has a question. She says, are there any weird climate or weather consequences of having such similar lengths of day and year?
Here's something that's cool because Mercury, there isn't really any weather, I wouldn't say, but because they orbit so elliptical and because those are similar to each other, there is a period of time near aphelion, the farthest Mercury gets from the sun, where the motion of the sun reverses in the sky, and so it's setting in the east and rising in the west for a short period of time because it's basically moving around the sun slower than it's rotating.
That's pretty cool. Awesome. All right, so Raquel has a question. It's what can this help us learn about planets around other stars?
Well, so if the planets are if they are airless, some of these same processes will be going on. They will be bombarded by solar wind. They'll be bombarded by solar photons and dust. And so you see some of these. I think there have been searches looking for like sodium tails around some planets. Because also if you have sodium in the atmosphere or on the surface, they can escape and form a torus. Io has this Io has this is what I wrote my thesis on, a banana-shaped, this is Io behind me if you didn't know that. It's the volcanic moon of Jupiter. And it has this torus-shaped, it's a banana-shaped cloud of sodium that leads and trails it in its orbit around Jupiter. And so you could see big tori of dust or ions around stars form from their planets. And Jupiter, Io also has this plasma torus. It's a full ring of plasma that happens because of its interactions with Jupiter. And so you could potentially see something like that. I don't know how hard. I imagine it would be very difficult to observe, but maybe someday.
Cool. So you mentioned that in the surface-bounded exosphere, that is a collisionless region. Is it
right.
collisionless because there's so few things and they're so separated? Why are they not colliding at all?
Yeah, it's just because they're so separated. The formal definition is the mean free path for collisions is greater than the scale height. And what that means is the mean free path between collisions is a measure of how often things collide with each other. And then the scale height is how quickly the atmospheric density drops off. And so if you have something going, moving upwards and it has escape velocity, it's more likely to escape than it is to hit something, to hit another atom, another species. So okay. Yeah, it's just because it's so thin. When you knock it off the surface, if it doesn't have escape velocity, it's most likely to return to the surface.
Okay, so if I were being like a real stickler, there could be some collisions. It's not necessarily absolutely collisionless, but it's like negligible because it happens so rarely.
Yeah, that's a better way of putting it.
Okay. So you also mentioned that oxygen is hard to observe. And again, as someone who writes about space settlements, we're always trying to figure out where the oxygen is. What makes the oxygen so hard to observe?
It's so the for resonance scattering, the kind of emission we're looking at, it has a line. Oxygen has a line in the far ultraviolet, where the sun does not put out a lot of far ultraviolet light, and so there aren't that many solar photons for it to scatter, basically. And I think also the scattering probability, like the probability that the atoms will absorb the photons, I think that's also relatively low. So there are other oxygen lines. This is just neutral oxygen. It's not molecular oxygen like we have in our atmosphere. There are other neutral oxygen lines in the visible, and those are like auroral lines. I think green or red. I think the green auroral line. I think is oxygen. I can't remember, but that's excited by electrons from the solar wind, making it down to denser parts of the atmosphere. So those kind of emissions are stronger. Those are auroral emissions, and those are stronger. And potentially, we could see signals from that in a planet. And those are still, and that again, that's in the upper atmosphere where we have atomic oxygen. I'm not sure how you observe molecular oxygen. There's probably infrared bands, but I'm not really sure how to. Europa has a molecular oxygen atmosphere, and we can observe that when electrons dissociate, break those O2 atoms apart, and they emit as neutral oxygen. So that's how we observe it at Europa. But Europa is another really a surface-bounded exosphere where it's very, very thin and it's being constantly bombarded by plasma. And so we're able to see it that way. Observing oxygen, I think, is a difficult problem.
I mean, so to me, this all seems like difficult. I can't. The fact that we were able to get data from something so close to the sun kind of blows my mind. And so, what was the hardest part about getting these data? I mean, probably getting the funding was the hardest part. But
yes, I didn't join the mission until shortly before we went into orbit. But getting to Mercury is very, very difficult because you're trying to get into an orbit around a small body that with the perturbations from the very large sun. And so you have to have your velocity exactly matched. And so in order to get there, I'm trying to remember how long it took to get there. I want to say it took 7 years, but it launched in 2004. I have a slide. Yeah, it launched in 2004, and then it did an Earth flyby, 2 Venus flybys, and 3 flybys of Mercury before it was able to go into orbit. And there's a European Japanese mission. It's a joint mission between the European Space Agency and the Japanese Space Agency called Bepi Colombo, which is on its way to Mercury now, and it's taking years, and it's going to take years to get there. It's had done several flybys of Venus, I think, so far, and then it has Mercury flybys, and that's a really much more ambitious mission than Messenger was. Bepi Colombo has 2 spacecraft. There's the Europeans built the Mercury surface observer, I forget, but it's going to be 2 spacecraft that in orbits that are in circular orbits, at different altitudes, much closer to the surface. Messenger's orbit was very elliptical because the spacecraft got really hot it's on the day side, and so you have these long cooling off periods, and especially when Messenger was really close to the surface on the day side, then it get heating on the instrument side it has the sun shield, which works amazing. It was room temperature on the backside of the sun shield, and 1,000 degrees on the front. But we get heating on the spacecraft from the surface. Mercury shining on the spacecraft would heat it, and that caused some thermal issues. So I'm not really sure how Bepi Colombo is handling that, and it'll be interesting to see how it works.
But did Messenger run as long as it was supposed to, and was the hard landing a planned landing?
It was inevitable because there's solar. I talked about solar radiation pressure, but there's also there's other kinds of ways of having radiation pressure, like a solar sail, and so solar sail effects would degrade Messenger's orbit, and so they had to do altitude bumps every once in a while, and eventually they ran out of fuel, so the orbit degraded.
Well, this was fascinating. As I mentioned, I've been working on this book, and it was not on my radar that Mercury had an atmosphere at all. And so you've probably saved me from being wrong in some future nerd conversation. So I really appreciate that. And yeah, thanks for your presentation. I think
it has no atmosphere to speak of.
Sorry?
Let's say Mercury, kids shows or kids books. Mercury has no atmosphere to speak of. And I get angry at first, and then, yeah, maybe they're right. I say that I study the atmospheres of things without atmospheres. That's generally how I describe my research.
It's a very mysterious way of doing it. I like it.
Hey, thank you.
Yeah. All right. Thanks. So if you could stop screen sharing, and I'm going to introduce our second speaker. So next up, we have Sarah Preston. She's presenting Sedimentology on Mars. Sarah is an undergrad at Rice University, so we all have this Rice University connection. We've all either been there at some point or are associated with it currently. She's an undergrad majoring in Earth, Environmental, and Planetary Sciences, and she works in the CBOC lab. So if you'd like to start sharing your screen, Sarah. Her fun fact, are you able to share your screen?
Oh, I can, yeah.
Okay. And her fun fact is that she can sort of do an ollie on her longboard sometimes. And as someone who can sort of walk up the stairs without tripping sometimes, I'm super impressed by that. How long did it take for you how long have you been on the longboard, and how long did it take to be able to sort of do an ollie sometimes?
So I started teaching myself, well, I don't want to say teaching myself. I started learning how to longboard in like September 2020, August 2020, I don't know. And then I was like, cool, I'll buy one. And then I got a longboard, and then 2 weeks later I broke my leg. So since September 2020, minus like 2 months, should have been longer, but I ignored my doctor a little bit. And I was like, I wish I could do skate tricks. And I can kind of do an ollie sometimes. It doesn't really work on a longboard because they're too big and heavy and awkward, but it would be a fun party trick if I was ever, I don't know, into going to parties. So.
Well, the last couple of years haven't been very party conducive, but is your leg doing okay now?
Oh yeah, it's fine. It like bends and everything. I can walk. We're all good.
That's good. I'm glad. All right, let's hear about sedimentology on Mars.
All right, cool. So sedimentology on Mars. Graphic design is not my passion. That is a theme you'll recognize in this presentation. I have never made a good looking PowerPoint, but I tried really hard on this one. So yeah, here is what I wanted to start off with, which is thinking about geology. Usually, unfortunately, geology gets kind of a bad rap in like the US education system. Earth science is only a required class in a few states, and it's usually like, here's what you take in 9th grade to fulfill a science requirement. It's like a blow off class that like you don't learn anything, everything's really boring. And I think that's really sad. So here's a picture I took in December of last year. I was at a field camp in Death Valley, California, which is one of the more Marsy environments on Earth, kind of. And I think this picture is really cool because you get to see a lot of geologic history in one place. There's all these extensive histories of folding and faulting and tectonic deformation that I don't know that much about because I'm a sedimentologist, and everybody else there was like, oh yes, I know everything about tectonics. And I was like, I don't care about tectonics. But we have often, like, you think of geology, you think of like, oh, it's just the science of rocks. And then like the fields most closely connected to what I do, sedimentology, it's like, oh, you look at sediment. And then stratigraphy is like, you look at stacks of rocks. Geomorphology, you look at stacks of rocks, but like they're hills. And all these definitions are correct, but they're really boring. I like to think of geology as storytelling. So for example, this picture, you see a cool rock. It looks like it has the anarchy symbol on it, which I think is why I took a picture of it. But there's no context. It was like in a parking lot. So we don't know what story that rock has. It's like if you have like, I don't know, a paragraph of text from a novel and it's in the middle of another novel. And you're like, well, I don't know what this is talking about. It's kind of cool to look at, I guess, but like, what does it mean? Other than apparently anarchy. So hang on, I was gonna start a stopwatch so I could keep track of my time. So one of my professors, I was like, yo, Cynthia, do you want a cool rock? And he's like, oh yeah, like where'd you get it? And I'm like, I don't remember. And he said an important sentence, which is, a cool rock with no context is just a cool rock, which I think really speaks to like how much the storytelling aspect of geology becomes important. And then here we have, this is another picture from field camp, these ridiculously convoluted folds where you had some rocks that were originally nice and horizontal as rocks like, or sedimentary rocks like to be. And then Death Valley is like a very complicated area. There was all of this folding and faulting and extension. And it ended up with a lot of rocks looking kind of like this, where they're folded this way and then it's folded that way. And sometimes they're folded on other folds. And another thing that I like to highlight about geology is it's not all about knowing what kind of rocks you're looking at. It's something I say a lot is, I don't know what kind of rock this is. People ask me like, Sarah, what kind of rock is this? And I'm like, well, it's either igneous or metamorphic, or it's metamorphic or sedimentary. Good luck. And people are like, oh my gosh, like, how do you do anything if you don't know what the rocks are? And the answer is, it doesn't matter all that much knowing exactly what every kind of rock is, as long as you know, like, what story do they tell all together? Like, I can tell you what kind of rock this is, other than probably igneous. But I can tell a little bit of its story because we have these veins of this white mineral here. And then similarly here, I honestly do not remember it's a sedimentary rock. I can't remember any of the characteristics of the sandstone, but the like point of that story that these rocks are telling is the tectonic history of the area. So now the question is, why do we study other planets? And Mathieu Lepotre and some other people wrote a cool paper in 2020 that's like probing space to understand Earth. So their main points were, we have other planets as analogs for Earth. On Earth, we have plate tectonics, which is pretty cool because it enables life in some really interesting and complicated ways. However, it's like Earth invented all this stuff and was like, oh my gosh, destroy the evidence. It's like trying to burn it. So we lose a lot of information every, like, I don't know, 10 or 100 million years as like all of the plates, not all the plates, but like the oceanic plates subduct under each other and everything kind of disappears eventually. So we don't know that much about what it was like to be a planet in the early days of the solar system. Like, yeah. On Mars, however, we don't have active plate tectonics. And if we had plate tectonics, it hasn't been for a really long time. So all of the stuff on the surface is really, really, really old. Like the sediment that I look at is about like 3.4 billion years old, I think, which is really stinking old. We also have other planets as experimental test beds, which I think is an interesting way of framing that because we don't control any of the variables like at all. You also have to get very creative and very well funded to collect data because we have to send spacecraft to it or have really, really good telescopes. And then we get not fantastic high quality observations because it's hard to take really good pictures of something that's several million miles away. So there's experimental test beds. It's like we can fiddle with about variables like gravity, atmospheric density, like what kind of sediment we're looking at, things like that. And also other planets as archives. Whatever it was ran into the Earth and the moon kind of flopped out. And then Matthew's talking about like if Mercury records information about solar processes. I was a little fuzzy on that part, I apologize. I don't know how the sun works. And then why study sedimentology? I feel very strongly about this. Here we have a text from one of my lab mates who said she was excited to think about sediment transport again. We have this when I saw a bunch of sand in a parking lot around campus in the middle of the night. And I was like, oh my gosh, there's a big pile of sand. You get lots of opportunities to make Star Wars memes. I'm a big fan of this one. I disagree with Anakin Skywalker on many things, including disliking sand. And then we have this picture, which I took on a field trip to New Mexico. A few people were trying to take a selfie, and Cindy, who is this guy in the baseball hat here, was like, oh, are you guys trying to take a red dirt selfie? And I said, oh my gosh, Cindy, do you want to take a red dirt selfie? Well, look at how excited we all are about red dirt. Dirt is pretty cool. But if you call it dirt in front of most sedimentologists, they'll yell at you. But I'm one of the cool ones, so we're good. And also, like, I don't know, I really, really like thinking about sedimentology, which sometimes I'm like, I feel like I like this a weird amount. But then I remember there is no normal amount to care about sediment, which is very freeing. I'm from Tennessee. There's no desert, there's no beach, it's landlocked, it's temperate. So lots of soil, but not lots of like sediment or exposed rock. So over like the shorter spring break we had in February, I think, I went to San Francisco to visit my aunt and uncle. And imagine my shock and awe when I found out that there's a beach like, I don't know, an hour away if you take public transit and like 15 minutes away if you don't. And I thought that was so cool. So I took lots of pictures and videos of sediment doing sediment things. So then final question, I guess, is why do we study Mars? It's more interesting than the moon. This is my personal opinion, but I stand by it very, very strongly. It doesn't eat spacecraft alive like Venus does. Like we can't send anything to Venus that lasts for any decent amount of time. It's kind of sad because Venus could be very interesting in terms of sediment transport because we get to see like what Earth-like gravity does if you have a really, really, really dense atmosphere, but oh well. It's pretty close by and easy to get to. Asterisk number one is compared to moons in the Jovian system and Saturn system. And the two asterisks are, it's easier than Venus because again, spacecraft can actually land there. Easier than any asteroid or anything because spacecraft can land there. Easier than Mercury for reasons Matthew went over. And OMG, just look at it. I mean, it's so beautiful. Like, I just can't get over, like, sometimes when I'm like really just about everything, I'll just pull up a picture of Mars and I'm like, wow, I get to study this. It's so cool. So put them all together. Why do we study sedimentology on Mars? We can test predictions about sediment transport. That one was first because it's the one nearest and dearest to my heart. My research focuses on determining grain size distributions in a unit of sandstone in Gale Crater, which is where the Curiosity River is, and trying to figure out like, okay, this distribution seems like it's different than what we have in active dunes. Why? Does that mean something about the, like where the sediment came from? Like what the atmosphere was like that could have transported the sediment? And right now the answer is pretty much like, I don't know, because turns out sediment transport is really complicated. And I'm getting like Stockholm syndrome into fluid mechanics now, apparently. We can study Mars's paleoclimate and paleohydrology because we can tell some cool stuff about like what type of sediment would be transported if we had a river versus just some really strong wind. What does groundwater alteration do to sediment? How do really strong winds or different atmospheric conditions affect how things blow around? Also habitability. I feel like I always have to say this one. This ties very much into the last point, but people tend to care a lot about living things, which couldn't be me. I just like my sediment. And then we also get a better understanding of processes that happen in Earth's deserts, which I think is kind of funny. We usually think of like these places as like on Earth as analogs for places on Mars, but I like to think of it as the other way around sometimes, where we have like these Martian things that we've seen. Like we have meandering rivers that we don't see that much on Earth without vegetation, with the exception of Death Valley. We see like mud cracks, we see bed forms, which are like dunes, ripples, anything that's like a large pile of sediment when there's a fluid moving sediment. So there's a lot of stuff we can find out about, like, is Earth normal or is Earth exceptional, if that makes sense. How do we do it? We have some options. There's rover observations, my personal favorite, orbital observations, field work, modeling, experimental work. The field work is terrestrial analogs. We do not have people going to Mars for spring break at this point. Yeah, so here's like some examples of things we can see with rovers. These are pictures from some of the cameras. This is a picture from Mastcam, which is, you think of the rover as like a car with an arm sticking out of it, or like an emu head. It's the camera on the head of the emu. And then we have Molly, which is a really, really high quality camera that takes really, really close up pictures of rocks. That's on the robot arm on Curiosity. So a little bit of stuff about the rovers. I do have enough time, I think, if I go over this fast, I can figure out how to like get this file into the PowerPoint. But some of the instruments that we use are Mastcam, which, okay, this is a bit of a pain to move, but in the MAST, we have Mastcam, which is a camera that takes pictures of broader areas. We have ChemCam, which has both a laser-induced breakdown spectrometer and a camera that takes like really, really high resolution, but also kind of goofy looking pictures. It's like if you taped a quarter to the wall behind me and tried taking a picture of it, you could see the dude's head, which I think is kind of nuts. We have on the arm, we have Molly and APXS, which are assisted by the DRT, which stands for dust removal tool. Molly takes the really, really close-up pictures. Most of the pictures I look at are an area that's about the size of a postage stamp or two stuck together. And then APXS is alpha particle X-ray spectrometer, which gets some bulk chemistry or bulk composition data. And then somewhere, I don't know where because I never look at it, is a drill that provides material for ChemMin, which finds mineralogy. But we also can find things out just through like the rover itself. Like, how does dust accumulate? Like, I think there's magnets on one of the instruments somewhere to help see if we can accumulate dust like that. Is the dust magnetic? The wheels, the way the wheels break, the way the wheels like can and can't drive over things, that can tell us stuff. So it's really cool. And something that I think is kind of interesting personally is that some of the instruments are just straight up broken. Like the drill doesn't really work anymore. ChemCam doesn't focus anymore. But the planetary scientists and engineers who put all this stuff together are so creative, and they've come up with so many ways to like work around things and sometimes get even more data than we expect out of the instruments. So I remember like when I was getting into planetary geology for the first time, I was going to reading group and I was like, I don't know what this paper is talking about, but this is so creative. Like, this is such an interesting way of going to the problem. Cool, so let's went through all that. This is a fun little thing. There's, hang on. Yeah, one of the tools is the DRT dust removal tool. I always say dirt by accident, which removes dust. Dust is a huge pain in my butt personally. It makes it hard to observe surface textures, which makes me very sad. So what can we observe from all these instruments? At the grain scale, we can observe mineralogy, bulk composition, the size of the grains, the shape of the grains, angularity of the grains, sphericity, roundedness, surface texture. So all this to say, like, how big is the grain? Does it have like little edges? Is it round? Is it not round? Are there like, well, this is less applicable on Mars because we can't get imagery that's higher resolution than I think like 13 microns per pixel. But in some instances, we can see surface texture, like do the grains show pitting? Are they flaky? And then at the scale of the rock, so like kind of intermediate between individual grains and outcrops, we can see sorting of the grains, sedimentary structures. Like I don't have a picture in this PowerPoint, but there's cross stratification, which is where you have like layers of sediment with like, I can't explain this well with my hands, but we can see things like flume structures, which help tell, oh, hang on. I'm trying to think of things I can explain easily without a visual. But anyway, so sedimentary structures, you can look them up, I'm sorry. We can see variations in chemistry or mineralogy that might occur like from grain to grain or from like little parts of the rock to other little parts of the rock. And then at the outcrop scale, we can see layering, deformation. We can also tell stuff about grain size based off of like how much of the outcrop sticks out versus how much has been eroded. We can see the spatial extent of geochemical alteration. And then what is this? Oh, hang on, skipping a slide. What story does this tell? From the grain scale observations, we can tell transport distance, we can tell depositional processes, provenance. So like, where did the grain come from? How far did it have to go to get here? What cemented it in place? And all that together, what does that say, like wholesale, about the environment? And we can also tell stuff about the extent and timing of bodies of water, geochemical alteration, so on and so forth. And all of that together helps tell us about paleoclimate. So it's like, what's happening on Mars now? What used to happen on Mars? How does what's happening on Mars now make it harder to observe what used to happen on Mars? So as an example, the outcrop I looked at, the Simpson sandstone, here are some of the images. We can tell from not really these images so much, but some other images that I look at, that the grains are generally like pretty well sorted. They have a bit of a bimodal distribution where there's a lot of like fine to medium sand grains and then some coarse grains. The grains are really well rounded, which is indicative of aeolian transport. So they've been blown around by the wind. We can tell that there's some layering of more resistant layers versus less resistant layers, which we can see here from, there's layers that you can see and layers that have receded so far that you can't see them anymore. And that helps, that's like a proxy for grain size. Larger grains are more resistant. Also, we can see that like there's other sand piled up on top of some of these layers here. We can see that here we have some really, really fine grained area, and then we have some really, really coarse grains. So this tells us that there was some mud here. How the mud got here, I don't know just from looking at this picture, but that could be a question to ask with imagery of the broader area. We can tell that most of these grains, oh, I forgot to say color, but most of these grains look pretty similar in color. So we know they're probably mostly similar in composition. We can see, I'd have to zoom in, which I don't know if I can do right now, but some of these grains show pitting, which is also indicative of aeolian transport. So lots of cool stuff like that. Okay, groovy. And that is both my time and my presentation. So thank you so much.
So you have absolutely, oh, first of all, I see you have orange juice now. So now we're both juice buddies. But you've made me regret that I did not take geology at all. I have somehow managed to never take a geology class. And between you and my buddy, Callan Bentley, who comes over and tells me about geology, I now am totally sad that I didn't take geology. And so I am one of those people who would probably call sediment dirt. What is the oh, also, it was great to see Sinti Lee. I love Sinti. He and I co-taught a bird class. You can never get enough Sinti. But anyway, what's the difference between sediment and dirt?
No, you cannot.
Yeah.
Fantastic question. I don't know. I have heard those terms. I'm not gonna say interchangeably, but mostly different based off of like context. Where usually you have like geologists will say like, oh yeah, this sediment. And then non-geologists will be like, oh my gosh, my car is covered in dirt. So they might mean the same thing, they might not. As far as I can tell, most of the difference is that sediment is much more of a scientific term than dirt.
Okay, so the difference
it's also
is
just funny to call it dirt sometimes, see people get riled up.
Is it like
I use the word regolith.
Sorry, go ahead.
I use the word regolith in my talk, and regolith is also just another word for the surface rocks and dirt.
But
this is
but like, so dirt would have like bacteria and other stuff in it, right? Whereas regolith is a certain kind of dirt, right? Because it's like jagged and sharp, and if you breathe it in, you're screwed. And like, It's different. That's different in a meaningful way.
I would call, I don't know. I would call any surface rocks the regolith. We think about it on the moon or Mercury or things where there isn't any water, but I don't think that's necessary.
Okay.
Mars has more interesting dirts because it has real clays. I think there's actual clays on Mars because there used to be water and things like that.
Ada, real quick, wants to show you the artwork that she did.
Hate to say it, but like between Mars, I think
I dried
my computer's being really
the
slow.
moon with grass on top of it because I read that moon rocks hold information about ancient Earth. So I thought that would be good for picture.
Groovy. I love it.
Lesson learned. Nice work. So Matthew, did you have a question you wanted to ask?
Yeah, I was wondering, it sounds like you're working mostly with just one instrument, or I guess one with, which rover are you working with?
So I work with data from the Curiosity rover. Okay. The instrument that I use the most is MAHLI, which stands for Mars Hand Lens Imager. The A doesn't stand for anything because why do we care about having acronyms make sense when we have robots on Mars, I guess. But I also use some data from two of the chemistry instruments, ChemCam and APXS, where they're both spectrometers. One's laser-induced breakdown spectroscopy. There's alpha particle X-ray spectroscopy. And then I also use some data from two other cameras. ChemCam, in addition to having a spectrometer, also has a camera. And then MassCam, actually there's two MassCams, but we're gonna pretend like it's one camera, which gives good context imagery.
Yeah, I was wondering about the context imagery and how if you see like a synergy with the orbital data, in seeing really where the regions you're looking at fit in on the global scale.
Yeah, so I study like this one particular unit of sandstone, and I don't remember what exactly it's supposed to look like from orbit. Other people who are much better at mapping and thinking about orbital scale things have done all this work. And unfortunately, the scale itself of the outcrop is a little bit, or not the scale, but the shape of the outcrop and how it like overlies the outcrop underneath it, or not outcrop, the, what in the world? Like the unit of rock underneath it, it's kind of difficult to tell. And somebody did all the work to map it. And like, there's a paper that was in revision and everything. And then lead author on the paper gets selected to be an astronaut. And the paper is lost to the revision process. And that's the story of why I feel personally victimized by the NASA astronaut program. But she's going to space like next month. So I guess it's worth it. So yeah, I'm not like too familiar with orbital scale anything.
Hopefully when she gets back, she'll be down for dealing with revisions.
Apparently, like the second, I think, author on the paper is like starting the process back up again. So I'm very excited for this to happen. Fingers crossed it's soon.
I'm keeping my fingers crossed for you. So we have a question from the audience. Raquel, or maybe Rachel, I'm awful with name pronunciations and I apologize, wants to know what is the scale of the pictures you showed? And thanks for the question. That's a good question.
All right. Most of the pictures that I showed of, actually, hang on, I can share my screen again. That's the thing I can do. If I remember where I put my PowerPoint. Okay, cool. Let's see. So this one really far. This one, I don't know. We have Kasky for scale here. And then moving into these pictures, I don't know what the scale is on this one. This was from a different paper. This one, oh, come back. Okay, yeah. The black circle, I think is either, I think that's 0.75 centimeters across. I don't have scale bars on these. Let's see, can I draw a line on top of this? I cannot. Oh no, I can. That line is about 1 centimeter in the real world. I had scale images, or not scale bars on images I used for my poster that I presented in December that I worked very hard on, was very proud of. And then I proceeded to forget to put scale bars on anything else ever again. But most of the pictures I look at, it's a scale of like 30 microns per pixel, and it's 1600 by 1200 pixels. And I've done the math before, but I forgot most of the numbers, but I think they're usually about like 5 centimeters across in the long direction. So sorry, that's not like a more satisfactory answer, but it's the same similar scale in these 3 images as well.
Yeah, so you had mentioned that we can get information on like grain size and grain shape and maybe not grain pitting, but to be honest, I had no idea that Curiosity could zoom in that close. And that's really awesome. Like, do you get to choose, like, we want to zoom in here, or have all these images been taken already and you're working on them in, or, a backlog or something? How does that work?
So all of the images that I use have been most of them are taken in between 2014 and like 2017. I have about 0 input on where anything goes with the rover. My PI is I don't remember if she's a participating scientist or on the science team for Perseverance. Those things do mean different things apparently. And then one of the grad students in my lab is working on ops for Perseverance over the summer. So I might be able to slide one of them a 20 and be like, hey, you should look at this, but also not the right rover. So there's a very long process that goes into picking all the science targets. A lot of people argue about it for a very long time. And something that complicates it a little bit is the camera that I use the images from. It's on the robot arm of the rover, which I'm about to embarrass myself here, is incredibly hard to plan out. So you're taking pictures, say this is the rock, the camera needs to be, this is the camera, it's usually about that far away. And it's on the end of an arm, a very heavy arm that is awkward to maneuver. So they have to go okay, we're gonna go like that, and then that, and then that, and that. So it takes about a day, I think, to take observations. The 2 instruments, MOLLE and then APXS, or its spectrometer counterpart, they're on opposite ends of the head. So you'll have the rock, and it'll go and then it'll go. It takes about a day or so to plan all this out. So we can't take that many extra pictures of whatever we want. We also can't take pictures, or we can't take as many pictures of things that aren't pretty flat. The spectrometer, it's only really good at taking taking measurements of flat surfaces. So if it's not a flat surface, the spectrometer is kind of in trouble. The camera can still work, but the point of the camera is to provide context for the spectrometer. So you get kind of stuck in a loop. So that's an interesting way to get data in a way, is what do we not have pictures of? That can tell us a little bit about what we'd expect the properties to be for something that isn't flat. So I wish I could drive the rover, but I can't even drive a car. So kind of an L. I work with Kirsten Seebach.
No, I don't know.
Yeah, she's relatively new.
Yeah, I mean, I've been mostly out of the business for the past 6 years since I moved to Space Telescope. And I know some geologists, but that's not really my focus.
So if you're trying to study sediment transport and you're to some extent limited to areas that are flat so that the camera and the spectrometer can work together, does that make studying transport difficult because sediment that's been moved might not be likely to also be flat? Or does sediment, I don't know anything about this stuff. Is that a major limitation, or is that not actually such a big deal?
So kind of yes and no. So one of the rules that we have for sedimentology, stratigraphy, how rocks like to stack on top of each other, is they'll stack on top of each other and be horizontal, because that's the lowest potential energy, is if everything's nice and flat. I have piece of paper and a pen. I don't know what I think I'm going to draw here to make anything make sense, especially because I'm not that good at drawing, but oh well. So when you'll have these layers of rocks, and then you'll have some process that cuts through the rock. It might be on Earth, it might be the river going through the Grand Canyon or something, but it'll cut through the weaker material, because again, it's easier to do that. And that will generally be the stuff that's finer grained. So if you have some variation in grain size. Generally, like the larger grain size will be preserved better than the finer grain size. So if we have like an outcrop and then stuff is like scooped out of it, we'll have generally like the bottom will be the flat part. It'll be like most resistant to erosion, I believe. I could be wrong on this. I haven't tried to explain this like this before. And then on the walls of the outcrop, like you'll have larger grain sizes will make like nice like ledges, I guess, that stick out a bit farther than the less resistant stuff. I figured out something I can draw, except you might not be able to see with this pen. Okay, yeah, I don't know if you can see anything here. Yeah, you can, okay, cool. So if we're looking at this side, this is gonna be like the largest grain size, the most resistant, or it might not be like the largest grain size. On Earth, for example, it might be held together with plant roots. This stuff will be the least resistant, which is usually the finer grain size. And then the stuff down here just it either hasn't gotten around to getting eroded away yet, or it's just not going to get eroded. It's more resistant.
Were these sediments laid down by water, or is it mostly wind processes?
Wind processes. So I'm not that well versed in the stratigraphy, which is like the description of like what rocks are stacked on top of each other in what order and what are they all like. But the Stimson overlies the Murray mudstone, which is deposited in a lake environment. And that's like really fine grains, like we're talking mud type of deal. And we have some sedimentary structures that are indicative of like a low energy water environment. And then we have the Stimson, where we have like the grain size is a good evidence of aeolian transport, and then also like the sedimentary structure. I'm gonna draw this again. So we have what's called cross stratification, which is where we have like these bounding surfaces. And then we have like kind of tilted layers in between. So these might be like the surface of a dune, and these might be the surface of ripples. And the ripples, as they move, we have like different layer or like mini layers, I guess you could call them. So that's most of how we know that the Stimson is aeolian, is because we have this beautiful, beautiful cross stratification that I unfortunately do not have any pictures of on deck, but I can also pull up a picture from a paper. Let me see.
So while you're looking that up, this is probably a technical term, but did I hear you say that it got there by alien transport?
Oh, aeolian, E-O-L-I-A-N. Sometimes spelled with an A at the front if you're British. Sorry.
Oh, that's right. I was like, oh, I wonder what that means in this context, because I can't mean what I think it means. But yeah. Anyway, all right, great.
Yeah, no, aeolian means just means wind.
Got it. That makes sense.
Let's see. Is this a good one? Here's a good picture of like crossbedding in the wild. This is from Bannerdahl 2018, which is a very long paper. It's 50 pages that goes into fantastic detail about like the bed form morphologies of everything in the Stimson, and starts talking about the grain scale stuff, but not as much as I would like. But we see there's like these bounding surfaces, which are dashed in yellow. And then we have these sets of like gently dipping like mini layers that go down to the right. So we see lots of this all throughout the Stimson sandstone. We don't see this that much in other parts or other outcrops in Gale Crater. So we see like, okay, something was different here from the stuff below it and the stuff above it.
Cool. So I have a question for both of you. So, calcium in the Mercury exosphere and sediment transport on Mars, those are like pretty specific things that probably is not like exactly what you said when you were 5 years old and thinking about what you wanted to do when you grew up. So how did you both end up here and studying these particular things? How about Sarah starts?
Okay, cool. So when I was in like second grade, we were learning about fruits and vegetables and what the differences were. And I was like, this is so cool. Oh my gosh. And I knew from then I wanted to be a scientist, and I wanted to be a botanist until I was in like 7th grade, which is a slightly weird like career aspiration for a 9-year-old, but you know what? You do you, I guess, past me. And then I kind of cycled through like every field of STEM of like what I was really interested in high school. And then I get to college, I'm like, I'm going to major in ecology, evolutionary biology. I put earth science as like my third choice. And I was like, I'm probably not going to actually do that because it sounds kind of boring. Spoiler alert, I do not find it boring. And I'm also not an eBio major. Apologies to Scott Solomon, who is not here. I have a severely overdue assignment for his class that I need to finish. And over the summer 2020, I was trying to figure out like, what kind of research stuff do I want to do? And I went to a few different reading groups held by professors in my department. And one of them I went to, I was like, wow, I feel nothing but apathy towards this, which means I feel nothing towards this. And the other one was planetary reading group. And I was like, this is so cool. I don't know what they're talking about like at all, but this is so cool. I was really drawn by like the creativity that everybody like showed in coming up with what to do for the papers, how cool everything looked and all the imagery. And so I started working with Kirsten Seebach in August of 2020. And originally I was going to work on grain size stuff like over winter break, like just do some measurements and then carry on with whatever else I was doing the semester before. And I'm still doing grain size stuff. And I'm like, wow, this is great. Sediment is so cool. So yeah, kind of like just tripped and fell and stumbled into it, but I'm very happy to be here.
Awesome. Yeah. Sorry, go ahead, Matthew.
Oh, well, I can do my story. So I guess I was always interested in astronomy, and then I took a planetary science course in college, and I really liked that. It's much more interesting to me than the galaxies, and that sort of, the real, the galaxies and cosmology and the things that people are usually thinking about. And so as in grad school, I studied Io atmosphere, and it's really interesting because it's hard. There's a lot of there's the plasma environment, plasma radiation environment is really intense, and Io has volcanoes, and that produces atmosphere, and it's being stripped apart by Jupiter. So I worked for a long time on outer solar system moons, Io and Europa. I worked with the Cassini plasma spectrometer team, which was an instrument on Cassini at Saturn, studying Enceladus, which is a moon of Saturn that has ice geysers coming out of its south pole. And so I was studying, what happens to the water that comes out of the South Pole. And then at some point, I think I just was, I needed funding. And so I started working with the messenger people, and that was right near the beginning of the actual data getting, as opposed to the waiting around for it to get there. And I've been working with them for 10 years now, off and on. I mean, and again, like I said, I burned out on the soft money research, so I don't spend that much time on it these days. But yeah.
And how is the James Webb data collection process going?
They are still working on mirror alignment.
Okay.
Is all I really should say.
Okay, got it. Still working on mirror alignment.
I can't talk about that.
Got it. Okay, sorry. But yeah, that sounds like a totally fun career path all along the way. Although I have friends on soft money who tell me that part is definitely stressful. But yeah, getting to think hard about all of these different systems is incredible.
Yeah, so I mean, I actually work mostly with the Hubble Space Telescope. I manage the software development work for the data calibration pipeline. For Webb, I'm one of the managers for the operators. I'm the deputy manager for that branch that does the operations. So I manage the people who do the operating. I manage the operators, but for Hubble, I'm really managing the software development, and so we're creating new products. Hubble's been in orbit for over 30 years, but we're still improving the products that we put out. And we put out a new set of products last year, and then hopefully by the end of March, I have a feeling it's going to be delayed a week or two, we'll be putting out these new products that combine. The idea is to combine, for different fields that have been observed many times, objects that have been observed many times over the past, essentially, it's just the active instruments. So essentially, I think 2003 or 2002 on, we'll be combining all of the observations from those instruments into single images. The pretty pictures that get published are mostly put out. Those are mostly made by the scientists, and we're putting out a lower level product that's calibrated. But these should be really nice new products that are science ready, scientists can use, but also look really nice.
So do you get to a point where you've worked on it long enough that like the awe goes away, or every time the data comes in and you're like, I'm the first person who is knowing this about this corner of the universe, is it still like a moment of amazingness?
I rarely look at HST data that comes in. I mean, there's really no reason. I have looked at some of the JWST stuff, but I think everyone who works there really likes the fact that they're working on these missions. You know, it's a lot. There are a lot of software engineers who don't have the astronomy background, and so they don't know might not necessarily know what these data are showing, but they're really proud of the fact that they're helping produce it.
Yeah, no doubt, it's awesome. Yeah, I mean, working on something like Hubble,
it's a good place to work.
Yeah, I feel like every day I would just like skip down the halls, be like, oh, I'm helping with this amazing thing.
Yeah, the Space Telescope is a very nice place to work.
Awesome. Well, good. I'm glad you like it. Well, this was a totally fun conversation about space. Was there anything that the two of you wanted to ask each other, or are we good? Did you both have the chance to ask the questions you wanted to ask?
Can I ask you a Rice question? What college are you in, Sarah?
Jones. I was about to ask you what college you were in too.
I was in Will Rice.
Oh man, okay. That's rough.
Okay. Yeah.
Well, these things are important. I unfortunately never was part of the colleges. I know Scott Solomon and his family, they were like the family that lived at the colleges. I don't remember what that's called. So it's a shame he's not here to also weigh in. But yeah, I missed that part of the experience, unfortunately, when I was at Rice. Okay. Well, this was tons of fun, and I really appreciate both of you taking the time to chat with us. I learned a lot about sedimentology, and I will make sure to not call sediment dirt, even though I'm not clear on the difference still. And I will be clear about Mercury having a little bit of an atmosphere going forward. And yeah, this was a ton of fun. I learned a lot. Thank you very much, both of you.
Yeah, thank you. Thank you a lot. I enjoyed this.
Good. I'm glad you had fun.
Thank you.
Hi, and what's the cat's name? Ada wants to know.
Oh, this is Ranger. He hates being on Zoom calls. He jumped in for like half a second earlier and then he ran away. He's like, oh my gosh, no, I'm not photogenic. He is photogenic, but.
Okay.
Yeah.
Bye, Ranger. Bye, Sarah. Bye, Matthew.
Bye.
All right, thanks, everyone.
Bye. Thanks, y'all.